Myself Dr. P. Vijayakumar, Associate Professor, Department of EC, Aditya University. In this session, we are going to see the definition of cross power spectral density and the properties of cross power spectral density. And we will be seeing in detail the proofs of the properties of cross power spectral density. At the end of this particular session, you will be understanding the definition of cross power spectral density, and also we will be learning one more learning outcome, that is understanding the properties of cross power spectral density. So, these two learning outcomes we will be learning at the end of this particular session. Okay. So in the spectral characteristics, one we have seen PST, another one is cross power spectral density. This thing we will see in this particular session. Okay. So, already we have seen what is meant by power spectral density. Power spectral density means it is a process of measuring the amount of power associated with the frequency components in the random process. Here the cross power spectral density is, we need to compute the power, or we need to measure the power across different frequency components associated over a different random process. Let us say x of t and y of t. So, over two different random processes, we are measuring the power spectral density, which is nothing but cross power spectral density. And we know the definition of cross power spectral density also can be computed with the help of cross correlation function. So, cross power spectral density is the Fourier transform of cross correlation function. So, this thing we will derive in the properties, the relation, and meanwhile we use this relation for defining the cross power spectral density. And cross power spectral density also further can be defined as limit t tends to infinity xt of omega, expectation of xt of omega into yt star of omega divided by 2t. So, here the two different random processes are x of t and y of t. Okay. So, sxy of omega also can be computed xt complex of omega, yt of omega. So, where xt of omega and yt of omega represents the Fourier transform of the two random processes x of t and y of t respectively over the interval minus t to t. Next, we also can compute the average cross power using the power spectral density. We know that the cross correlation function is nothing but inverse Fourier transform of cross power spectral density. Cross correlation function at tau is equal to 0 is mathematically equal to cross average power, and which is also mathematically equal to area under cross power spectral density over a given bandwidth. The bandwidth is d omega. It can be from omega 2 minus omega 1. So, the power spectral density property and cross power spectral density property are pretty much similar. So, Sxy of omega is equal to Sxy of minus omega. What does it mean? It is an even function of omega. And also one more parameter is there, Sxy star of omega. Okay, all these are mathematically equal. Second property, the real part of Sxy of omega is a even function of omega. Sxy of minus omega, real part of Sxy of minus omega is equal to real part of Sxy of omega, and both converse is also true. This is true only for real part of cross power spectral density, and the imaginary part of Sxy of omega and Sy of omega are odd functions of omega, and this is true only for imaginary part. So, generally imaginary part means sine term, sine is an odd function, real part means cos term in e power j omega. So, cos is an even function of omega. We can easily remember very easily. So, real part is even function of omega, imaginary part is odd function of omega. Next one, fourth property, if two random processes x of t and y of t are said to be orthogonal, if they are orthogonal, their power spectral density is mathematically equal to 0. Sxy of omega and Sy of omega will be mathematically equal to 0. If random process x of t and y of t are uncorrelated and they have constant mean values x bar and y bar, then Sxy of omega is equal to 2 pi x bar or y bar of delta omega, 2 pi x bar into y bar into delta of omega. And the last property is cross power spectral density and the time average cross correlation function are Fourier transform pairs. This relation is also called as Wiener-Kinchy relation. Wiener-Kinchy relation. We will see the proof for this particular relation, very important, and we will be very frequently using this relation in solving the problems and in computing the parameters. So, with simple this relation we can compute average power, we can compute autocorrelation function, we can compute the power spectral density. All three can be computed using a single relation. So, the first property is Sxy of minus omega is mathematically equal to Syx of omega or Sxy conjugate of omega. Let us prove that one. Syx of omega is equal to, so as per the mathematical definition of cross power spectral density, Fourier transform of cross correlation function Ryx of tau is equal to e power minus j omega tau. So, Ryx of tau can be written as expectation of y of t into x of t plus tau e power minus j omega tau d tau. And what I am doing is here also can be written as expectation of y of t, here can be written as expectation of x of t into y of t minus tau. Both relations are correct. So, here this expectation of x of t into y of t minus tau also can be written as Rxy of minus tau. We know that the cross correlation function is an even function of tau. Cross correlation function is an even function of tau. Rxy of minus tau is equal to Rxy of tau. So, this is equal to Sxy of minus omega, or mathematically this also equal to Rxy of tau e power minus j omega tau whole conjugate. So, which is equal to Sxy conjugate of omega. So, this is the first property of cross power spectral density. Next, the second property, the real parts of Sxy of omega and Syx of omega are even functions of omega. This also we can prove very easily. So, the real part of Sxy of omega. So, in the real, so we know as per the Euler's relation, e power j omega tau can be written as cos omega tau minus j sin omega tau. So, the real part of e power minus j omega tau is cos omega tau. So, that is nothing but Rxy of tau into cos omega tau. Now, we will apply the verify whether it is even function or not. Sxy of minus omega means in place of omega I am placing minus omega. We know that the cos an even function, cos is an even function, cos of minus omega is equal to cos omega. So, Rxy of tau cos omega tau, which is mathematically equal to Sxy of omega. So, the real part of Sxy of omega and Syx of omega are even functions. We can prove the same manner, this one also. Next, imaginary part of Syx of omega is an odd function and vice versa. So, first we will write the mathematical definition of Sxy of omega. So, e power minus j omega 2 can be written by using the Euler's relation cos omega tau minus j sin omega tau. So, the imaginary part is sin omega tau. So, now I am keeping minus omega, sin of minus omega. Sin of minus omega will be sin omega. So, sin is an odd function. Sin is an odd function. Sin of minus omega is equal to minus sin omega. Sin of minus omega is equal to minus sin omega. So, what you will get minus. So, clearly this is an odd function of omega. F of minus x is equal to minus of f of x. Since sin is an odd function, so the overall function also will be odd function. In the earlier property, cos is an even function, that is why overall property is an even function of omega. Next, last relation, Wiener-Kinchy relation, very important. So, this is the definition we used for all the properties. Here we will see what is the relationship between power spectral density and cross correlation function, cross power spectral density and cross correlation function. Let us take two real random process x of t and y of t. Now, I am truncating the samples over a time period minus t to t. I am taking only the samples over the range minus t to t. So, that is nothing but xt of t is equal to x of t, truncated version. Similarly, yt of t is equal to y of t only over this limit minus t to t. Now, we know the Fourier transform of this one, Fourier transform of this one. This is the mathematical formula. And the cross power can be obtained by using the formula 1 by 2t minus t, xt of t, yt of t. Okay. And the cross power, we are applying the expectation on both sides, and we know the Parseval's relation. Based on the Parseval's relation, energy spectral density can be related with energy. So, we replaced it with x of t and y of t, we replaced with 1 by 2 pi using Parseval's relation, 1 by 2 pi minus infinity to infinity xt of j, yt star of j omega d omega. So, we can write pxy as expectation of this one. Okay. And we are taking expectation inside. Expectation of this function is mathematically equal to sxy of omega, sxy of omega. So, sxy of omega is mathematically defined as limit t tends to infinity expectation of xt of j omega yt star of j omega, which is nothing but cross power spectral density. So, the cross power spectral density formula, and in this formula what we are doing is x of t, y of t plus tau e power minus j omega tau. And this is mathematically equal to time average autocorrelation function. This is mathematically equal to time average autocorrelation function. So, the time average autocorrelation function is nothing but limit t tends to infinity 1 by 2t minus t to t r xy of t comma t plus tau dt. This is nothing but the time average cross correlation function. So, sxy of omega is the Fourier transform of cross correlation function. So, if it is a stationary random process, simply it will be equal to rxy of tau. If it is a Whiteson stationary random process, sxy of omega is equal to Fourier transform of cross correlation function rxy of tau. Okay. So, this Wiener-Kinczi relation is very important, and we will see the problems related to Wiener-Kinczi relation in the next session. So, we will compute the cross average power, we will compute the cross power spectral density, we will compute the cross correlation function using this Wiener-Kinczi relation. So, this relation is very useful in solving the problems. This property is very important. So, in this session what we have seen is, we have seen the definition of cross power spectral density, mathematical definitions. 3 definitions we have seen: sxy of omega, expectation of xt star of omega yt of omega by 2t, limit t tends to infinity, and one more definition we have seen with respect to cross correlation function, and with respect to power we have seen all these relations of cross power spectral density, mathematical definition. And also we have seen the properties of cross power spectral density. The first property is sxy of omega is equal to syx of minus omega or sxy star of minus omega. Next, real part of sxy of omega is an even function, imaginary part of sxy of omega is an odd function, and finally we have seen the Wiener-Kinczi relation in the properties of cross power spectral density. Okay. So, in the next session, we will be solving the problems related to cross power spectral density, and we will be seeing how to compute the different parameters using the properties of cross power spectral density. Okay. Thank you.